Hey guys, welcome back to the shop. We're going to jump on our next machining project today. We've got another part that we need to machine for our pump customer, and that is this guy right here. We need one of these. This one's got some wear and they want it replaced. I don't know exactly how it's used. I can tell you what it's called though, according to the print. It's called a steady bearing bushing for automatic or manual combination. But this one has got some wear on it, so it actually it accepts a number 6211 ball bearing, and it has worn out, and then somebody over time actually used some green Loctite to hold it on there. So they would actually like to have this part replaced. All right, I've actually got a print for this one too that they provided. That was made in February of 1987. It's got all the schematics on here, all the dimensions that we need to know. And this was originally made by the Amarillo Gear Company. Whenever I was at Motion, we used to do a lot of gearboxes, a lot of gear reducers that were made by Amarillo. We always called them the armadillos, but that just kind of brings back a little memories from the gearbox shop there. So yeah, we've got to make this part right here. They did supply this piece of material. Don't know what the grade is, so we're just going to call it some mystery steel. But it's probably, if I had to guess, that's going to be some cold rolled, 1018 cold rolled steel. So we're just going to make it out of that since they provided it. So it's going to be some basic lathe work. We are going to use our Precision Matthews lathe today. We'll have to do some facing, drilling, boring, turning. We have a snap ring groove to machine in here as well. We'll have to part it off, do some facing to get it to the right length. And then we have a keyway to broach on the inside. And then there's also a key slot on this outer face here that we got to mill in there as well. All right, so we'll head over to the hide mech and get our piece cut. This is a little bit too long to go in there right now, so I'm going to go ahead and just kind of cut it where it needs to be. And then we'll head over to the manual lathe and get started on it. Just getting the saw ready, and I was pulling the chip pan out, and I can tell that the coolant level is a little bit low in there. There's a sight glass on the back of it so you can see where it needs to be. So I'm going to go ahead and pull my hose over here for our mixing unit, go ahead and get some more coolant in here. Because this, the one complaint that I've got from the saw is that if this coolant sump is not topped off completely, it'll start cavitating and kind of missing. You guys have probably seen that in some of the previous videos. But as you cut and it makes chips, I got myself backed into a corner here. The screen is right there and all the chips pile up on that little screen, and then it keeps the coolant from washing through this pan down into the sump, so then it starts starving and cavitating itself. So that's the only issue that I've really had from the saw right here, but I've kind of learned to work around it now. But anyway, I'm gonna get this guy topped off so we can cut our stock. My hose reel will just reach the hide mech over here. There's a 50-foot hose on it. Yeah, there we go. It'll just run down into the sump, and then I'll monitor the back of it. There's a sight glass. Funny enough, it's on the very back, so you gotta get back here behind it and be able to see the sight glass. This is our mixing unit back here with our 50-foot hose reel. And then we are using our trim microsaw 685 XT. It's what I run in all the machines. So the mixing unit just siphons that up, and it actually pulls in city supplied tap water there, mixes it, and then sends it up and out to the hose reel. Really nice, effective unit here. Just monitoring it and then having a look right down here at that sight glass. Oh, just starting to come into the sight glass now. All right, just shut it off. We should be topped off there right where we need. All right, should be good to go. Now both of those saw cuts on this piece are pretty crooked. And one thing that this hide mech does do very, very well is cut nice straight cuts. So we're just going to go ahead and trim this in just a little bit. And we're basically just going to cut it in half. I asked them, they have a lot of this kind of material over there at their shop. I asked him if he would just cut me a chunk long enough that I could make two. I like having enough material for a backup in case I screw that up, and we have another one that we can make. So that's what they did. So we'll basically just cut it in half, and that'll give us enough material to be able to chuck it good and not hang out too far either. All right, here we go. Really putting some coolant out this morning. Slow it down a little bit. It's getting all over the floor. When you get to the bottom of these cuts, you gotta be careful with your feed because it'll wow. It was screaming at me right there. That's why I got this pocket on my shirt so I can keep my earplugs handy. Got a nice beautiful cut there. What I was saying was that when you get down to the bottom of these rounds there, there's not much material there that it's cutting. And if you're feeding it too fast, once it gets down to the bottom, it is likely to damage one or even more of the teeth on the bandsaw blade. And as it comes through, it just kind of rips it off there, and it might. I'm using a carbide tip blade, so I don't want to mess up one of them carbide tips because I hate having to change the blade. But just something to keep in mind when you're feeding, when you get to the bottom of these rounds, you might want to slow your feed rate down so it doesn't come through so fast. I think this was just over 10 inches long, so we may just cut it in half. Let's see. Yeah, that's 10 1/4. So we'll just measure out 5 1/8 and just cut this piece in half. Right about there. That looks good. I'm gonna have to take this 6-jaw apart one of these days and get those threads, the scroll cleaned out. All right, let's see. Yeah, we've got about 3 1/16. Our part is gonna finish 2 5/32, so 2.156. So that's going to give us enough there that we can turn it back and still be able to part this off. So we should be good to go here. Let's see how everything looks spinning. Yeah, it looks good. That's machining pretty nice right there. I bet you what we have is some 12L14. If that's the case, that's highly machinable material. 12L14 has lead added to it just to increase the machinability. And that's what that's looking like. Yeah, that looks good. Go ahead and set our 0 right there. I believe I'll start with just kind of roughing it down. So our OD is going to be 2.5 inches, and I'm just going to verify that with our part here. Yep, so we have a 2.5 inch OD on the part, and then I believe this was 3 7/16. Yeah, so we have a good bit of material, yep, to come off of that. So let's just come on back here and set a 0 at how about 2 3/4 of an inch. All right, we'll set a 0 down here on our mag back indicator. All right, I think that's going to work pretty good. I'm just going to go ahead and set a 0 here. And then once we get it, we're gonna rough the OD, get it close. We're gonna go ahead and drill the ID, get it close, cool everything down, and then we'll carry on with our finishing. So let's see how this guy's gonna machine. Get our feed set. So this is gonna be 11 thousandths per revolution right here. And we'll go ahead and take 100 thousandths a pass. Just makes it easy to keep up with because there's a 200 thousandths resolution dial. That should put us at an OD there of about, it was 540, 2.540. Yeah, 2.540. So that gives us about 40 thousandths to clean up that OD. We do have a little turning to do here, but I think we're going to go ahead and focus on getting our hole in there and getting it cooled down. So we'll set up a drill chuck, we'll spot it, put a pilot hole in there, and then I have this is a 1 3/16 taper shank drill. I've got a fresh grind on that drill right there, so it should do a good job. And then we'll, after we cool it down, we'll go ahead and bore it to size. Finishes at 1 1/4 inch bore. We'll spot it with this 1/2 inch spotting drill here. All right, our short link drills really isn't quite long enough. I give you a good 2 inch depth there, maybe a little more. So we're just going to go ahead and we're going to go with our jobber length drill today, 1/2 inch. How about we use some of our flood coolant today for the drilling here. Move our carriage back, make this a little bit easier to get in there. Check our depth with our thin steer it rule. 2 5/8. We'll go about another 1/4 inch for that drill. Puts us 3 inches deep. It should be good to go. I'm almost certain that that material is 12L14 steel. If you guys have never machined that yourself and you're looking for some stock to machine some components like this, consider that if you can use it, because you can see how easily it machines. It, you know, puts out nice manageable chips. It's not hard on your tools, whether it be high speed or carbide. It's pretty easy to machine. So it's a nice material to work with as far as the machinist goes, having to machine components. Now I will say that if a part has to be welded on, you don't want to use that material at all. But if you're just making a part, 12L14 works pretty good. All right, so let's get our drill chuck out of here, and we'll put our taper shank drill in. I need to do a little more cleaning on this, but this is the first time I believe I've used this exact drill in the Precision Matthews. And one thing that I did was go over it with our Precision Flatstone. You can see all these little dents that are on this taper shank there, these little high spots. That's where the Flatstone really kind of helps you out on taking those little dings down, so that whenever you install it in your Morse taper socket here, it's not putting little dents and scratches in there as well. Got the lathe set at 180 RPM. That's a good speed for using these larger drills here. All right, we are cavitating on our pump. I'm gonna have to top off our sump. I think we're getting a little stopped up down here. I got to get this chip pan cleaned out. All right, running a little low on coolant, so let's get that figured out. 2 machines in one day, we're having to top off here. Yeah, it is a little bit low in there. I can't pull it out because it's still draining out of the chip pan there, but we do need to top it off a little bit. So I'll just sit here with the hose and just top this thing off, and we'll get back to it. It's amazing how fast these coolant sumps can evaporate. The water in it will evaporate before you know it. Especially in a shop like mine, we keep the climate control, the AC's going to keep the humidity level down in here so that it's comfortable to work in. And I think that just kind of adds to the evaporation of the water in the sumps. All right, that looks good. That's plenty of coolant. About an inch from the top of the pan there. All right, I think we can get back to our drilling now. Turn our pump back on. Yeah, sounds much better. See how aggressive I've been drilling this hole. There's our bottom right there. Go ahead and clean it up. You can certainly push these big taper shank drills pretty hard, especially manually like this. But that's another reason why I like drilling a pilot hole, which usually for me is about a 1/2 inch if we got to open it up any more than that. I usually start with a 1/2 inch pilot, because what that does is remove the material from where the chisel point of the larger drill is having to cut. It just makes it a lot easier to push these bigger drills up into a hole, especially when you're getting up, you know, say 2, 2.5, or even 3 inch in size on these drills here. So pilot hole for me, it's just how I like to do my work. I have seen people that refuse to use a pilot drill because they said it's just a, I don't know, you got your own reasons why, but some people didn't. They told me you shouldn't have to drill a hole and then drill another hole and another hole. But for me, I just like busting out the center of it to reduce the pressure that it takes for the chisel point of the drill to work. So it just makes it easier to drill. So one thing I'm going to do is just go ahead and it's not really hot. It is still warm. But we're going to run this in low and use our coolant and just go ahead and get it. Turn the pump back on. Let our coolant cool the workpiece down like that. Usually only takes a minute or two and it's good. Okay, we've got our part cooled down. We're going to go ahead and bore the size. We're shooting for 1.25 inch, and they did give me a tolerance to 1 to 2 thousandths over 1.25 inch. So we're going to be shooting for a size of 1.251 to 1.252. And before we start, let me go ahead and see where that drill, I never even measured it after we drilled it. And you can see the drill, it cut it over about 7/8 thousandths. So right around 1.195. So about 55 thousandths. I've already got it touched. I've already got a Z depth established there. So let's just take 20 thousandths. I've got my feed set to 5 thousandths per revolution. That particular material, it's easier to get it to break off the chip. So it's doing well. I've got a 0 established up here. There's our chips. Leaving a nice smooth finish in there. That tool's doing good. And let's use my telescope gauge to get a size on here. This particular tool still causes a lot of controversy in the comment section. It just really amazes me how many people have no confidence in this tool and how it's used, or that it can give you accurate readings. If you know how to use it, it'll measure it exact. All right, 214. So yeah, we still got a little ways to go. All right, let's give this a measurement and see where we are. May have a couple of cuts left to make. .233. I'm going to do that again just to kind of compare. See if we get that 2 times in a row. 1.233. All right, so basically got like 18 to 19 thousandths we want to take out of there. So what I'm going to do is I'm going to split that. We're going to make a 10 thousandths pass in there, and then that'll be about equal to the final pass. So let's take a 10 thou pass, we'll measure it, and then we'll take whatever we need for our final cut. It should put us at 1.243, and that finish is really, really nice in there, nice and smooth. $143.5. Go back up in there a little bit further. Just check this again. It's got a good feel right there. Yep, 0.243.5. So that's going to give us about 7.5 thousandths is what we want to take. I'm going to shoot for the low end of the tolerance there, so that we have a thousandths leeway. All right, so did we hit our target? I'm shooting for 1.251. Let's see if our telescope gauges are going to tell us the truth today. So far, that's looking pretty good from my perspective. .251 and 5/10. According to that measurement, I hit it exactly in the middle of my tolerance, which is good. That's what I want. Go in there and measure it one more time. I'm not looking at the numbers. I'm not trying to make it read what I want it to read. I'm going by feel, and you can see that telescope gauge just hanging in there. All right, and that time I got 251 and 6/10. So I got 1/10 difference, which is normal for manual measurements like that using a telescope gauge. But this tool, once you get familiar with it, you get comfortable using it, you know the technique. In order to get it directly in the center of the center line there, this will give you accurate readings. And once you establish the feel that you have to be able to, I take my middle finger and thumb on the fixed anvil of the telescope gauge, and I rest it right on this anvil of the mic. I try to keep in the center, and I take it and I just rock it. I rock it back and forth like that. And you use your pointy finger here to bring the mic down gently at a time. Don't squeeze it until you feel that touch. When the telescope gauge rocks through there and you feel it touch your mic, there's your measurement. And if you practice that enough, you'll get really accurate measurements using these two tools right here. I'm just going to go ahead and give this a chamfer using a brazed on tool. And now we can go ahead and focus on getting the OD to size next. All right, so the next dimension that we're going to work on, we're going to go back to the OD. We're going to get this area turned. This is where the bearing journal is right there. You can see how it slides on there, so it's a little undersized. All right, and if you keep it straight, it'll come off there. So this print here, this is the drawing they provided, and that's going to be this dimension here, 2.1654 plus or minus 2/10. All right, so that's going to be for this bearing here, which is a 211. This one's a Fafner bearing, but I've got my bearing chart right here. This is SKF, and if we look at 211, in this case it'll be 6211. All right, there's your shaft diameter maximum, minimum, 2.1655 to 2.166. So according to the SKF chart, that's going to give you a 5/10 or a 1/2 thousandths tolerance on your bearing journal. 2.1655, and we were looking at 2.1654. So this is, well, they've got a much tighter tolerance on this drawing than this bearing chart shows right there. So that just gives me an idea that we're going to just shoot for what they've got on this, but it's all going to be good. They are getting a new bearing, so they're going to have a brand new bearing to put on there. And as long as we get the fit like what it says on these charts, it's going to be a proper fit for a ball bearing. We also have to machine a snap ring groove. That's what retains the bearing on there. So once we get this journal turned down, they want the journal in front of the snap ring turned down to 2.57. So we'll turn that, and then we'll put our snap ring groove in there. So we'll do all this turning here on the outside, and then the last thing we'll do is worry about that snap ring groove there. We should be down to 2 finishing passes on our journal here. So let's see where we're at right now, and we're going to split it in 2. So right now it's measuring 2.190½. Let me just do that one more time just to double check. That's exactly 2.19. I'm coming to my calculator. 2.1905 minus 2.166 equals 24.5 thousandths. Okay, so what we'll do is split that into 2. I'm going to take 15 thousandths, and then we're going to mic it, and then we'll take our final cut on there, which should be right around 9 to 10 thousandths. Should be our final cut now. We'll do our final measurement. .177. .177. I'm just double checking because I'm gonna dial it in and hopefully we're gonna land on our size there. All right, 2.177, and I'm getting 2/10 over that. All right, so I am gonna shoot for the maximum 2.166 according to my bearing chart right here, and that'll give me, you know, a 1/2 thousandths that we can hit it with some emery if we need to bring it down just slightly. Okay, did we hit our mark? We're looking for 2.166 or 165.5. We are at 2.166 and 2/10. Perfect. All right, so that lets me know that we're in good shape. We can go ahead and carry on, and all we got to do is take a piece of like 400 emery and hit this just a little bit. It'll take a little bit of those the tool marks down just slightly, and it's going to fall right within that tolerance that we're looking for a 211 bearing. All right, good deal. All right, now we're going to focus on this OD here. This is 2.5, and we've got 40 thousandths to come off of that. I'll just go ahead and get this one moving here. Get my indicator out of the way. I'm just going to come in here like that. Set a 0 on our Z. We'll just touch it and take it in 2 cuts there, 2 20-thou cuts. Just trying to improve the surface finish with some of my dark cutting oil here. All right, where are we at? 20 thousandths, exactly 20 thousandths. We got exactly 20 thou on the mic there to bring it down. And that one is not a super critical dimension like the bearing journal is. It's even called out as a fraction. But the original is 2.5, so that's what we're going to make it. And now I'm psyching myself out, so I'm going to measure it one more time. 20 thousandths. All right, I'm going to dial in 20, 10, 20, maybe a half over right there. Now let's go for it. Yep, so we got it 3/10 over on that measurement right there, which is good. Same thing right there, 3/10 over, 2.5. We did good. All right, next up, we've got our snap ring groove that we're gonna focus on. And we've got some good dimensions on this drawing right here. We've got a shoulder length called out of 827 thou plus 10 thousandths minus 0. We have a groove diameter in there of 2.57. I mistakenly looked at that earlier thinking that that was turned down, but that's actually your groove diameter that we're focusing on there. And then we have a groove width, 86 thousandths plus 2 minus 0. So I've got one of my Walter MX22 threading tools set up. We have a 1/16 wide grooving tool. It measures exactly 62 thou. So we can plunge that in there and then we can just step it over the, what was that, 24 thousandths needed to get it widened out. All right, so let's knock that one out next. Don't let it rub, it'll chatter on you. There we go. Now we'll step it over. Offset at 24 thou. See if we can get some caliper measurements on this groove here. Shooting for 86. I got 85.5 right there. That's probably going to be just fine. It says 86 plus 2. Our snap ring groove, our retaining ring fits in there just fine. All right, let's see. Our OD, our depth, I'm sorry, from one side. Try that again. We do have a burr on there too. 55 thousandths. According to my calculator, we got 2.056 on our groove diameter, so we are good to go on that. So that is finished up. I need to do some chamfers on here, and then we need to do just a slight amount of polish in here as well. All right, just about through, but we need to touch up this journal, remember. And measure it again. We're looking for a maximum of 2.166, and we've got a few tenths to come down. I'm going to use a strip of this 320 grit. You can see the material right there on the paper. You can usually get a few tenths off pretty quickly because it's knocking those high spots down at the tool marks. All right, so 2.166 right there, so that's already got it. 3 tenths. I'm gonna hit it one more time. All right, let's see if we landed on it. 2.165 and 7 tenths right there. So that is that's putting us 1 tenth over the tolerance that Amarillo have on their drawing. And I think that's going to be just fine because that falls within the ball bearing fitment specs. I'm just measuring it one more time. And 7 tenths. So I'm going to call that good. We landed it right where we need to be, the higher side of the tolerance for the bearing fit. So that new bearing, when it goes on, hopefully they got a bearing warmer and they can warm it up and it'll just drop right on there. And what I was taught years ago as to why these dimensions are so critical for bearings is not only does the bearing need to fit right, because a lot of bearing applications you don't want the bearing moving. You need it captured on the journal, but it doesn't need to be too tight that it actually causes this race to swell, even the outside race. And I was told also These dimensions that we go by in these charts, like this one's from SFK, is that the engineers have thermal expansion built into these dimensions as well. So as the bearing gets warmed up when it's in use, it's going to grow slightly, and you want your journals, your bores or your journals, to be still within spec so it's not loose at that point. So that's just what I was taught years ago, and that's what I've always kind of lived by, and it makes sense to me. But I'm happy with our fit for our 211 bearing there. Got my parting tool ready. We're going to go ahead and part this off. I'm going to part it 2 1/4 wide, and that's going to give us plenty of material to face off on that back side. I've got a piece of brass in the drill chuck here to catch it once it parts off. And I think we'll probably go ahead and use some coolant on this. Hopefully it won't make a huge mess for me. Let's see what that does. Not too bad. If there's anything that bugs me around the shop, it's material that has razor sharp edges on it so that you can just slice your hands wide open whenever you're trying to root around for something when you're looking for a piece of material. When I have drops like this that I know I'm going to save and put on the shelf, I just take an extra minute and go ahead and chamfer those edges so that I don't have to worry about slicing my fingers open. So we'll just do that. In fact, I'm going to speed it back up to our high range. Just knock them corners off. There's going to be times when you wish that you would have done that. It only takes an extra minute to do this. There we go. Take the tool out so you don't smash your finger against the cutting tool when you go to remove the material. I've seen plenty of people do that. And then there's our stock. Now, maybe since I'm showing you this, we'll go ahead and turn that around and chamfer that side too. Look at that bandsaw cut, nice and straight. And then the other thing that we can do is go ahead and get our marker. And I'm going to write on there what this is because I know that this is 12L14 because of the way that it's machining. And we'll just put it on here so we'll know what it is. 12L14. All right, last stop that we need to do is, for the lathe anyway, we need to face that other end. That chuck is tight. I got to get it apart, clean it. All right, we got about 100 thousandths to come off this according to my calipers. Our total length for our part is 2 and 5/32. So 2.156 is what we're hunting for. Just go ahead and get a measurement on this with our micrometer. We got a nice clean face there. 2.250 and a half. We'll just get a measurement with our mic on our width there, offset it, take one more cut. All right, that's 2.199. All right, we hit 2.156 and 6/10. We're within about a half a thousandths. I think that's good enough. Our print calls out for a 1/16 by 45 degree chamfer on this side. All right, so all of our lathe work is done. I'm real happy with the part. It looks good, it feels good. We hit all our dimensions just like the print wanted us to. So lathe work is finished. So the next phase of the project that we need to get on now is going to be this internal keyway. So this is a 1/4 inch wide keyway, and then you also have this wider keyway that's milled in this outer face there that we got to do. But I think what we'll do is focus on this internal key first. I've got to find my tooling. I packed up all of my broach tools, put them in a bin. I brought it down here. So I've got to dig through that bin and just find the bushing and the cutter and the shims that I need to do that. And maybe our green arbor press here will help us get this done. If it gives me too many problems, we'll have to go down and to the home shop. I've still got my electric press wired up and set up there, but we'll see how it goes. So internal keyway, and then the last phase will be this notch, this slot that we got to mill in there, right there.